So it's been a long journey. I've cried on this campus many times. One thing that I've learned, especially in the last year of doing the MFA program, was I found that no matter how much it feels like you need to pull an all-nighter, it's not worth it. Just go to bed. Take care of your body.
Solid advice.
So I was really interested in kind of the intersection of science and art. I really liked sort of the balance of left and right brain and the way that those things interact with each other. A lot of the ways that I understand mathematical concepts is through visualizing what they look like as a graph. And so that's kind of where my work has taken me. So two ways that I've been thinking a lot about how to visualize complex ideas, or especially abstract ideas, are analogies and anecdotes. So like communicating with cartoons a lot, so these are some. So scientifically and verbally, we a lot of times will use analogies, like when we're learning about electronics, we'll talk about electricity moving through a wire, like water moving through a pipe. Visually, we also have analogies, because any chart is really an analogy. We're visually encoding, saying that up is an increase of something, or change over time is moving from left to right. And these analogies are so sort of ingrained in our psyche that we don't actually think about them as the fact that they are visual encodings, but they're kind of universally accepted. Anecdotes are also really helpful for understanding abstract ideas. So when we talk about gravity, we have the classic story of the apple falling on Isaac Newton's head as a way of understanding how gravity works in the universe. Or visually, a lot of times we'll use anecdotes like illustrations or pictures to kind of tell a broader story with a simple image. Also, when we're talking about visualization and scientific inquiry, we kind of have a spectrum of graphics that move from exploration to explanation. And originally I was thinking that it was sort of like you start with an exploration and then you move to an explanation, but actually it's a lot more of a convoluted path where you're moving back and forth often. And this is something that I'm finding a lot in my work at the Complex Systems Center. So I kind of mapped the scientific method here to that movement from exploration to explanation and back and forth. And so when we combine those two things and we start thinking about anecdotes and analogies and then exploration and explanation, we might think of like a point sample as an exploratory anecdote. So we just take a random part of a data set and we look at that individual point to kind of help us understand or explore what it is that our data set is telling us. And then when we're looking at explanatory anecdotes, we might have a case study, so we may take a specific point sample that we think captures a larger narrative. Exploratory analogies might be like visual encodings, so putting things onto a graph and just seeing what it looks like. And then summary graphs are helpful for when we have a story that we've kind of pulled out from those exploratory graphics, creating something that would end up in like a scientific journal. So what I'd like to talk about today is some of those exploratory anecdotes and analogies and explanations. So the benefit of data visualization really can't be understated. Anscombe's quartet is a great example of this. So this is a data set, or actually 4 different data sets that when we do the traditional data science thing, we find a mean, a standard deviation, a correlation, a linear regression. And even though these data sets are very different, all of those summary statistics are the same. But all it takes is putting those things into graphs to see just visually how different they are, even though they have all of the same summary statistics. Autodesk did a great job also with the data source dozen. So this is 12 different data sets that all have these same summary statistics of mean, standard deviation, and correlation, but visually we can see that they're drastically different. So in my work at the Complex Systems Center, this is kind of my general visualization pipeline that I'm working with right now. I'm interested in learning new languages and methods for exploration. But this is kind of the one that I've been working with lately. So taking data from a database, bringing it into Python, and cleaning the data, and then Pandas is this really great library for Python that allows us to do data manipulation in terms of like a whole data set, instead of having like a for loop where you would say, for each item in this set, do this equation. We can just say, take this whole column, do this transformation to it, and then we end up with this new column. So it's sort of a much simpler way to do really large-scale data manipulation. Then once we've kind of done that sort of analysis, we can export graphics using Plotly and then render them in JavaScript and create interactive dashboards. But I actually think that before we even get to the beginning of that whole pipeline, it's important to just kind of come up with visual hypotheses. So a lot of times when researchers come into my office and we start talking about data visualization, they're kind of like, well, you know, what should I be using? Should I be using Python? Should I be using R? Should I be using MATLAB? And I kind of am like, well, let's take a step back and let's just sort of think about like, what's the story that we want to tell, or what's the question that we're asking? And we end up drawing on the board, and sometimes it ends up with something like this, where we've just got stick figures and we're trying to figure out sort of more holistically what's going on with the data. Another thing we like to do is experiments. So this is a personal experiment that I did where I took a graph with the same shape and applied it to 3 really, really different fields. So this is my Richter scales of life with emotional state, financial markets, and blood sugar, so sort of volatility-inducing events. And in the work at the Complex Systems Center, we have people working in all different fields coming together and looking at networks that are ecological systems, that are financial systems, that are healthcare data sets that seem like qualitatively they're really different, but actually quantitatively when we apply mathematical reasoning to them, we can model some of them similarly, or we can use similar strategies for really different data sets. So once we've kind of done that sort of brainstorming, then we start thinking about visual encoding. So what quality or what quantities can we map to visual representations? And these are just a couple examples of categorical and ordinal ways of visually encoding information that is numeric. This is crazy, actually. So the New York Stock Exchange now uses lasers to communicate its data across different points on Wall Street, and it's kind of restricted by the speed of light. So even though we like to think about stock exchanges as being instantaneous, there's actually a slight discrepancy just because of the amount of time that it takes for the light to travel across the space. And so this researcher came in and was curious, so like how would I graphically represent these transactional discrepancies? And he wasn't able to share the data set that he had with me, but we just sat down and talked about it for a little bit. And then I went back to my desk and I pulled up Adobe Illustrator, and without any data, I just kind of thought about like a dummy data set almost. So I was thinking like, okay, so if we have all of these stock exchanges, how do the prices change over time, and how might we visually encode that? Either with like a spatial dimension, adding hue, or just kind of like showing representational changes in the quantities of those data. So that was helpful for him because then he was able to sort of take that visual hypothesis back to his data set and create his own visualizations based off of sort of the conversation that we had. Obviously, visual encoding has some difficulties. This is a study of asking people to look at colors that they had assigned to a number and then guess what the relationship was between one number and another based off of the color difference. And so we can see here that this magma map, which was being used very often, when we got down to this low level, the amount of error rate in estimating the quantity of the data based off of the color was really high. And so then they moved to plasma, which didn't have this like dark range so much, and so the error rate went down a little bit. And then their final recommendation was actually this new color palette that they developed called Viridis, which is now part of a lot of data visualization color palette libraries. So that's another thing that's really important to remember is like any time that we're translating one thing to another, we have to take into account the fact that like as human beings, our perception factors into the way in which we understand colors and relationships. So another sort of case study of my movement back and forth from exploration to explanation. When we partnered with Mass Mutual Life Insurance at the Complex Systems Center, their data science team every year does this cool project called Data Days for Good, where they partner off into teams and they sort of take a break from their usual analysis and they just think about what's something going on in the community or something going on more broadly that we could sort of apply our data science skills to and give some insight into. So I was interested in doing a project on Vermont's compost economy because back in 2012 we passed this law called Act 148 that required that all businesses and households be composting all their food scraps by 2020. And this was something that was rolled out in like a phased plan. So by 2014, food scrap generators of 2 tons per week had to divert material to a certified facility, and then by 2020 we're going to move all the way down to individual households. And so every year we see more and more businesses with lower and lower food scrap tonnage being required to compost those food scraps. And so the Agency of Natural Resources has this really great data set where they actually started inventorying all of the places all over the state that all of the commercial places that are generating food scraps. And so without any coding, I was able to just download the CSV file that the Agency of Natural Resources had put out for public use, and then upload it to this user interface called Cardo, which allowed us to just put all of those data points onto a map that was interactive, that you could zoom into, and you could colorize things by what kind of food scrap facility it was, so food establishments, schools, nursing and assisted living, food manufacturers, hospitals, correctional facilities, and others. And that allowed us to kind of take those point samples and learn more about our data set broadly. Then what I did is I pulled that data set into Python and I started creating visualizations. And so this was a visualization showing the distribution of food scrap tons per week. So I actually had to exclude 2 places, Cabot Creamery and West River Creamery, because their amount of food scrap production was so astronomical that it actually made it so you couldn't see any of the rest of this chart. And so excluding those 2 things, you can see that most places have an extremely low food scrap production per week. And so when we look at this in terms of what that looks like in terms of the phase-out plan for the Act 148, we can see that the amount of tons per week added in 2014 was huge because there were a whole bunch of really big places that were immediately required to start composting their food scraps. And so this was the number of food scrap generators, and then this was the amount of tons per week that were added. And so we see year over year, the amount of tons per week being added is less and less, but the number of places is more and more, which means that volumetrically, it's kind of had a whole bunch being required initially and then it tapered off. But in terms of the logistics of trucking all of that food waste around, it's getting more and more complex because the number of generators being added is increasing. And so that's up to 2017. When we add in 2020, we see that the whole chart skews a little bit, and our tons per week added is pretty small, but actually the number of generators that are going to be added by 2020 is pretty significant. And so going back into Cardo, we have the same map that shows those food scrap generators that will be required by 2017, colored by the year, and then the red is the addition of all of those generators that will be required by 2020. So this kind of helped us draw attention to that fact, and so moving from an exploratory map that just showed the food scrap generators, and then just looking at that timeline and then trying to break down the generators by those brackets that the Act 148 had set in place, kind of helped us create a more explanatory graphic that drew attention to the fact that this is a logistical problem, not really a volumetric problem. So another example of my bouncing between exploration and explanation at the Complex Systems Center. Some of you may be familiar with the hedonometer. This is an interactive website where at the Complex Systems Center we get a random 10% of all tweets every single day. And a couple years ago we did this study where we had 100,000 people on the internet ranking the most 10,000 used words in the English language on a scale of 1 to 10 from how unhappy to happy they were. And then by taking those average rankings and then applying them to tweets, we were able to get these average word scores for every single day. So an example of how that works, we can see Thursday, November 23rd, 2017, this was Thanksgiving Day. So usage of the word Thanksgiving was up, which is a happy word, so it's usage of the word happy and thankful. And usage of the word Friday and friends and food was up. Usage of the word crying was down. Also not and tax were down. And then conversely, on Wednesday, November 9th, 2016, we had the election of Donald Trump as the 45th President of the United States, which, based off of our metric scales, ranked as a very sad day, mostly because usage of the word racist, not, hate, rape, and fear were all up. But there was also a shift towards the happiness because usage of the word one and America were up. So it's kind of an interesting metric. It's obviously somewhat subjective based off of people's ratings of how happy the words are, and also we're just getting data from Twitter, and so Twitter itself has a kind of unique demographic group that can influence those scores. Mostly English speakers also. So one of the things that we've been curious about is we're seeing story turbulence increase over time. So the amount of topic shift from one day to the next in 2018, it's kind of a hard metric to wrap your head around, but it's like, it's sort of like there are new trends coming in and coming out a lot more rapidly than we saw in the earlier days of Twitter, and that could be a combination of just the amount that people are on the internet and the amount that people are using Twitter, and sort of the rapid news cycles that we're seeing nowadays. So I was curious if we were also getting sentiment turbulence in addition to our story turbulence. So if the difference from one day to the next in terms of the average happiness for that day was increasing year over year. So what I did was took this chart, which was from 2009 to 2018, and basically chunked it up into segments of a single year and then plotted them on top of each other. So it gets a little bit messy, but what we can see here is like the daily sentiment towards the end of the year. This spike here is Thanksgiving, and this spike here is Christmas. I think Mother's Day is right around here. This is Valentine's Day here, so we're seeing sort of commonalities on the happy spikes, but a lot of variance on the low spikes because those are usually natural disasters, terrorist attacks, mass shootings, and other events that really are less predictable. So generally we're seeing that happiness is predictable, but unhappiness is a lot less predictable. So taking that daily sentiment and then translating it into a monthly 30-day rolling average was an idea that I had hashed with one of our researchers who does work with financial data, because this is something that they do when they're looking at financial markets to sort of smooth out this turbulence and see more general trends. So this is when you take any given day and compare it compare the 30-day average from that day and the 30 days previous to it to the next day. So it's sort of like you're taking a 30-day window and sliding it across. So it ends up smoothing out this curve a little bit. And so then we can start to see more visible trends in terms of year over year, how things are changing. So this is our yearly average sentiment, the deviation from total average. So this is if we take the entire year, we take the average happiness for the entire year, and then we compare it to the average happiness across all of the years. Obviously, this is an extreme simplification of the data, but it's just interesting to take a look at. And this on the bottom chart is the distribution of the daily sentiment. So when you see a really tight peak like that, that means that there's not a whole lot of variance, and when it starts to flatten out a little bit, that means that there's more variance in the daily sentiment. So then continuing on that visualization track, taking the distribution of the weekly average sentiment and then the monthly average sentiment, we really start to see some stratification of year over year how things are changing. So we can see that 2013, 2014 are sort of low back here, but a little bit more tightly distributed, whereas 2017 is one of our flattest years, which means that there's the most variance, especially in monthly average sentiment. So this is a plot just showing the daily sentiment change. So a lot of these charts were generated algorithmically. So what we can do is we can take a list of, I want all of the years, I want to do daily, monthly, and weekly sentiment, and then sentiment change, and then rolling averages. And by sort of creating a function that will generate these charts automatically, rather than having to code each individual chart, we can just sort of set those parameters and then have it generate a whole bunch of charts that we can then put into a dashboard and compare to one another. This one is just filtered to show only 2017, but all of these are interactive, so you can actually scroll over them and look at a specific day and see what was the date, what was the sentiment, and how does it compare to the other years, and you can turn on and off different years to compare individual ones. So this is an absolute value of the sentiment change, so not whether it went up or it went down, but just how much was it different from the previous day. And then looking at that sentiment change year over year, we can see this is the up and down, and then this is just the total change from one day to the next, what the average was. So taking, say, from today and then comparing it to yesterday, how much did our average happiness change? This is doing the same thing with the weekly sentiment change and then a distribution of that weekly sentiment change. So here we can also see how 2017 is one of the lowest, sort of flattest distributions, which means that there was the most change week over week, and then especially monthly, we can start to see that turbulence, which I think this is the chart that captures it the most. So it's basically saying if we take that monthly rolling average and we take the average sentiment change for each every day compared to 30 days previous, what that average was, 2017 has a lot more turbulence in terms of sentiment compared to other years. It's kind of a lot, so much statistics. Got some questions. One of the big projects that I've been working on is with MassMutual Life Insurance, and we have this huge data set, 2.5 million people by around 600 variables for people. So that includes demographic information, like their age and their gender, and then it also contains labs values, so what their blood pressure was, their height and weight, their cholesterol, urinalysis, a lot of different like blood tests, things like that. So when we're studying networks at the Complex Systems Center, we do a lot of work with graph theory. So graph theory is this interesting field of mathematics that deals with taking sort of theoretical problems and turning them into mathematical problems. So this is a classic example of the Königsberg Bridge problem. This was a question that came up, I think in the 1750s maybe, which was asking, there was this little island in the middle of a river, and then there were 3 land masses around the island, and people were wondering, for years and years, it was kind of this classic riddle, is it possible to traverse all of the bridges in Königsberg, this town, only once? And this mathematician, Leonard Euler, came up with the idea of putting these points into a graph so that we could better understand how to solve that problem. And by turning it into a graph, it was easy to see that it was not possible actually to traverse all of these bridges without crossing over any of them more than once. And so this is sort of the beginning of the study of graph theory, which has now been expanded to study a whole bunch of different problems with large data sets. And so this is the work of one of my colleagues, Laurent Hubert-Dufresne, who does research into epidemiology, so studying the way that pandemics spread. And he does a lot of work with understanding how networks function and how they change over time depending on their structure and their dynamical qualities. So whether or not, say, a node is replaced in a network. So if you think about like a school system, if a kid gets sick, that child is going to go home and they're removed from the graph. But if a teacher gets sick, that teacher goes home, but then a new teacher is brought in and put in their place. And so that replacement and then that substitute teacher leaving and joining another school network afterwards means that that node has mathematically different properties, and thus that network has very different properties than a network where there would be no replacement. And so when we're studying the way that like pandemics spread through a school system or across a country, being able to quantitatively evaluate how that impacts the way that things spread is really important. So one way that we kind of are better able to understand graphs is by creating these adjacency matrices. So this is an example of a very simple graph that has 6 different nodes, and then if we create a chart that shows each of those nodes compared to each of those nodes, but we can see that like, so A is connected to B, A is also connected to C, and A is connected to D, and actually this chart is kind of like the same this way and this way. It's like a mirror image of itself. So the dark points on the map are when 2 characters are in the same scene together. And so this is just another way of visually representing the same network in kind of like a more organized fashion. When we're looking at really large data sets, creating a network visualization can be really frustrating. The hairball visualization is a very classic one that we encounter often with complex systems. And so one of my challenges as a researcher in visualization is trying to combat that hairball problem and figure out other ways to visualize networks that help us understand them without getting kind of bogged down in the computational and visual complexity of them. With this data from MassMutual, one of the things that we're trying to figure out is, can we interpolate values? So anytime that people are applying for life insurance, it's really painful for the patient and costly for the company to have to take these labs values, to have to do a whole range of blood tests in order to predict what someone's mortality is like. And so if we're able to mathematically take demographic data, information that people self-report, then we can theoretically take fewer lab tests, and then it's less painful for the patient, less costly for the company, and just kind of all around better. but we want to be able to do that in a way that's computationally supported, because we don't want to be sort of willy-nilly making decisions about things without understanding where those decisions are coming from. There's also this rule in life insurance called no black boxes. So you guys might have encountered this before learning about machine learning, where it's like you put all of your variables in one end and then it spits out an answer at the other end, but there are all of these sort of hidden layers where we're not really sure what decisions the computer is making to give us that result. And so in the life insurance industry, we don't allow for our algorithms to make decisions without us knowing exactly why they made those decisions. Everything needs to be explainable. So one of the things that we've been doing is creating these correlation matrices. So rather than previously we'd seen all of these points in our data set kind of compared to one another and seeing where they coexist in space. But if we were to do that with our data set, when you've got 600 variables and 2.5 million people, we would need 600 football field-sized adjacency matrices to communicate that. And so instead what we do is we take the variables and we run a correlation algorithm. So for each pair of variables, this example just shows miles per gallon, cylinders, displacement, horsepower, qualities about a car data set. We sort of compare those to one another, and then we see that maybe the weight of the car is inversely correlated to the speed of the car, or that the acceleration is related to the miles per gallon. And so we're able to get like a correlation matrix that explains what the relationship is between each pair of variables. So this is, I've had to obfuscate the names of the variables here because our data is under non-disclosure agreement. But this is a correlation matrix of a subsampling of some of our variables compared to other variables. And then what I did was I coded up this slider that shows how well supported these correlations are. So for a lot of our data set, we have empty spaces. So we have places where people didn't have to take the test because they weren't required to. And so you may have, it will say, oh, this thing is really well correlated to that other thing, but that's only because there's just one person in the data set. And so if that one person answers true to both of these rarely asked questions, that means that our correlation is very high, but it's not well supported because only one person answered it. So by adding this slider in, we're able to kind of block out those values that look like they're important because they have a really high correlation or anti-correlation, but in actuality they're not useful because it's a very small sampling of the data set. So if we can kind of threshold how well the questions are supported, then we're better able to say, okay, these things are really well supported and 90% of our data set has answered both questions. So then taking that correlation matrix and the thresholding with it, we can create a three-dimensional network visualization like this that's a lot more simplified than our original hairball. And each node in this network represents a question, and we have a linkage drawn between the two questions if they're well correlated. And what ends up happening is we get these sort of like constellations that when we zoom over them, we find that maybe one of them is our smoking constellation, so all of the questions in it are related to whether or not people smoke. Or we have a diabetes constellation or a cholesterol constellation, so that kind of helps us understand what these relationships are and how some things are similar to other things. Of course, correlation can be misleading. Not only is correlation not equal to causation, but sometimes we'll see that there will be like a skewing. So this is an example. Try your energy drink. It's highly correlated with performance, and it's, very few people drink an energy drink that have low athletic performance, but then they have a couple professional athletes that they paid to drink a lot of the energy drink, and now they have this correlation value. And so it's really important in our research that we sort of think about the ways in which our summary statistics can kind of mislead us. Another example that we were finding in our data set was that some things were showing up as really well correlated if 90% of the people had answered false to both questions. We were getting these constellations that we thought were useful, where we were like, wow, like is lupus correlated to HIV, or like are they related somehow? And it turns out that, well, the correlation value was really high because most people had answered false to both questions. So now we're in the process of sort of filtering out, okay, I only want to know if the correlation is significant if the outliers, or the smaller portion of that population, kind of overlaps. So if the 1% of people who have HIV are the same 1% of people who have lupus, kind of thing, which is not the case. This is an example of that same adjacency matrix from Les Miserables that I showed earlier, but colored and sorted by clustering. So this is another thing that data scientists do often, using computational strategies to cluster their data into groups. And so I'm going to go through a couple of those quickly. So hierarchical clustering is one way that we'll get groups of things together. So this is where we sort of say, okay, find the nearest neighbor and put those two things in a cluster, and then find the nearest neighbor to those and put those things in a cluster. And so then what we can do is we create this sort of like tree structure that shows how things are related. And if we decide, okay, I want to have so many clusters, we can decide at what point we want to sort of cut this dendrogram so that we have different groups. So you can see these dotted lines here saying that's 5 clusters, that's 3 clusters, and then all the way down to 2 clusters, and then 1 cluster. Another way we do this is k-means. So this is where we put, in this situation we have to know already how many clusters we're expecting to have, which can be a challenge. But if we know how many clusters we need to have, then we can put those 3 different points randomly on the graph, and then just compute which point is closest to each of the individual points, and then continue to iterate on that. So once we've computed which one is closest for all of the groups, then we put the centroid closest to those ones, and we're able to sort of get these clusters by iteratively going over the data set and updating the cluster assignments. When we have more than like 2 or 3 variables, trying to visualize and cluster things can be challenging, and so one strategy that people use is principal component analysis. So this is where we take information, so say we had that correlation matrix, and then we wanted to sort of condense it down into a smaller graph. What we might say is, rather than saying, okay, I've got these 15 variables that are all related to smoking, we could sort of get like a summary statistic that was like 1 value for all of the things in the smoking cluster, or 1 value for all of the things in the cholesterol cluster, so that we ended up with a single value as opposed to 15 different values for each cluster. And then we could sort of cluster based off of those clusters. It's a little difficult to explain verbally, which is why I'm trying to do it visually. Yeah, so we end up getting like a vector quality, a quantity assigned to each sort of summary statistic, and then clustering based off of those summary statistics. This is another example of mean shift clustering, so taking sort of the average of different clusters and then separating them into buckets based off of those averages. And so all of these things are sort of happening in 2 or 3 dimensional space, but they're actually using summary statistics from much larger variable spaces. So this is sort of like a condensing down, because it's difficult if you think about, like, if the data set is 600 variables, what we're really talking about is a 600 dimensional image that we're trying to create. And we can't really think in 600 dimensions, or we can't see in 600 dimensions. what we're trying to do is sort of find those ways in which we can turn those relationships into like summary vectors and then create three-dimensional images out of those. This is another example. I just really like it because it's a smiley face. So this is dbScan, which works a lot better than k-means clustering or some of our other clustering algorithms for finding things that are not like circles. So like in this instance, when it's got like a line like this, k-means clustering would probably try to say like 1, 2, 3 or something like that, but dbScan is just another sort of algorithmic way of clustering that allows us to sort of follow the shapes similar to the way that a human might trace something. So it's interesting how, like, as a human, we would be very easily able to kind of just circle these things and be like, oh, that's a group, that's a group, that's a group. But actually, it takes a lot of thinking to communicate to a computer, like, this is what I want in terms of identifying clusters of information data. Yeah, dimensionality reduction is a real challenge. So this is, say we've got all of these points in three-dimensional space. How do we tell the computer that we want this image? So how do we tell it not to just flatten the whole thing, because then we would have these like red dots on top of these green dots and these blue dots on top of these green dots, but actually to sort of unfold the data set and put it down onto a two-dimensional space, which a good analogy for that is the trouble that we encountered when we were trying to take the globe, a three-dimensional sphere, and then flatten it out onto a map surface. So topology is really interesting. I've been doing more research into this in terms of understanding networks. So this is where we think about one of these networks not as just a series of nodes and linkages, but actually as like a shape that has a surface to it. So if each triangle of data points that are connected is actually a face, like a polygon, then we can apply the same sorts of thinking that we do to physical objects to data sets. So this is kind of an example of like all three of these objects to a topologist, which is a mathematician that studies surfaces, are actually the same. And so if we apply topological study to these networks, then we get these sort of like polygonal shapes that we can then do a different kind of quantitative analysis of. One of my favorite jokes is, what's the difference between an idiot and a topologist? An idiot knows the difference between a coffee cup and a donut. To a topologist, these are the same things because they're both just three-dimensional shapes that have a single hole through them. So all this to say that we're doing all of this data science, but it's really important to kind of go back to those anecdotes when we're making these visual analogies, and to remember that like each of these data points does represent a human being. And so this is constantly a discussion that we're having at the Complex Systems Center is when we're doing this large-scale analysis, what's being lost or what's being taken out, and how do we maintain that story, and how do we really stay grounded in recognizing that the conclusions that we're making algorithmically have real humanitarian impacts. So this is a video that I took at an open data science conference in Boston this past summer, where Microsoft had a demo of their facial recognition system, which had also a sort of like happiness scale analysis, and that was guessing the gender and the mood and the age of all of the people that were walking by, sort of without their consent. And then up here we have the facial recognition system that's linked to China's social credit score, which some of you may have heard about that a little bit. It's kind of like this singular number that's supposed to be sort of a combination of your financial credit score and your social trustworthiness score and a whole bunch of other metrics. And so that's something that we talk about a lot at the Complex Systems Center, is like, what do we lose when we're just simplifying all of these complex variables down into a single score. And some of you may have seen this Black Mirror episode where individual people are assigned a total score of, you know, how good of a person they are, how worthy they are, and sort of the dystopian effects that can have on society. So yeah, analogies and anecdotes, I think, are good ways of sort of framing the different ways in which we can communicate these abstract ideas. And then it's always important to sort of move between exploration and explanation, not just moving from exploration to explanation, but back and forth a lot. And any time that we feel like we have an explanation, kind of trying to come up with more questions and continue to explore from different angles. Thank you.
When you're working with really abstract kinds of methods and processes, do you find it, how easy is it to get back to explanations that are human, you know, that are kind of like everyday personal explanations for things? Like I was thinking, I really liked the analysis you were doing with sentiment and the volatility of sentiment. And I was thinking, you have all this really great information, but why is there so much more volatility today? You know, so how do you get to that kind of an explanation?
Yeah, so
and how hard is it to do that?
It is challenging, especially when we're kind of like in it. Like when we already sort of have this basis of like, oh yeah, we had all of these people rank all of these words, and then we took random 10% of all of Twitter's data, and then we ran it through this pipeline, and then we created this, you know, and like, so like we're already sort of like standing on this pile of stuff that we did, and like anyone that's coded has learned that like a lot of times when something breaks in your code, it's like something that you did like months ago that just like you keep passing that bug through, and so it's really helpful for us to sort of think about, okay, we have these summary statistics, but what does that mean for, like, in the same way that when we're designing like a user interface, we might think about user stories. So you might sort of get this like, oh, we have the information architecture, and these are the different sort of theoretical areas where things should fit, but then when you think about a user story, so like, okay, my name's Wendy, I'm 12 years old, and I'm thinking about applying to Champlain College when I'm 18, like, where do I start? Then you start to kind of realize, like, oh, I actually, like, your information architecture is not helpful to me because 99% of the stuff I don't need to know, and so we kind of think about tweets in the same way, or we think about our individual data points in the same way. So what does that mean for, say, this use case, or for this particular tweet? How does that sort of get filtered through our system, and how can we sort of like trace that user story?
So I'm going to add on to that. Are you able to disseminate from the information how people, because you were working with, I think, this insurance company, basically deciding, okay, these people get this because of these data sets, but can you determine sort of life choices, what choices people should make based on previous data sets? So if a general amount of people made these decisions and did these types of things, that becomes a data set. And then can you tell somebody who's, for example, to be a graphic designer, okay, these graphic designers did this. Is it possible to tell a future person, like, oh, if you have these types of skills or this type of data, you could potentially like choose this life choice?
Yeah, it's a good question, because so we're constantly talking about like correlation is not causation, and so like one of the most commonly used ways that life insurance companies price life insurance and predict mortality is based off of someone's smoking status. And one of the questions that we're constantly asking is it just that people who smoke because they smoke have such a lower life expectancy, or are there a whole bunch of other variables that smoking status is just a flag for? Like, smoking status is also related to if you haven't obtained a high school education. That's like a really good good chance that you're more likely to be a smoker if you haven't obtained a high school education. So then there are a whole bunch of other dependencies based off of that, like your access to health insurance and how many hours you work and what kinds of food you eat and things like that. So to tell someone, your predicted mortality is going to, you could add 20 years to your life if you just quit smoking. It's sort of like, well, if all of those other variables aren't changed also, then our probabilistic model is not actually true to your human experience.
Question, what about the tools that you use and how have you found that they're evolving quickly as you're kind of in this work? How have they evolved since you started? Do you find yourself having to really kind of write new methods and do a lot of bespoke programming work, or do you find that you're picking up new visualization techniques and methods of parsing information kind of from the spread of tools that are available to you?
Yeah, so I actually just started at the Complex Systems Center back in March, and so there hasn't been a whole lot of turnover so far in terms of the libraries and what things are supported. I can say though that when I worked at Dealer.com, they were having a huge problem with their digital display advertising with the change from Flash to HTML5. And so that was something where they thought that Flash would be around forever. It was sort of like the industry standard, and then all of a sudden there was this huge turnover. It wasn't supported by major browsers, and so they had to revamp all of their graphics. And so that's definitely a concern that we talk about often, or even with the switch from Python 2 to Python 3, if I'm looking at GitHub repositories that are older, even something as simple as a print statement is different from Python 2 to Python 3. And so it can be challenging to sort of keep track of what those subtle changes are.
Talk briefly to me about kind of the visualization of the data and kind of how we represent it, how we cluster it, how we can move from different dimensionalities of data, and also equally as important, the way you kind of parse the data. You did many iterations of the Twitter emotional state, and kind of different ways to slice it, break it down, and different ways to which numbers to include. How do you kind of which aspect of that do you find yourself more drawn to? Which do you find more challenging, or do you really see it as a very holistic kind of combination?
I really enjoy the whole process because it's very meditative. For me, it sort of feels almost like I'm untangling threads or something. Especially when you start thinking about code in terms of which variables are getting passed where. It starts to become less about the characters that you're seeing on the screen and more about these sort of models that you have in your mind of how data is moving through the system. I think that it's definitely challenging for a lot of folks who maybe only really like the beautiful picture at the end or only really like the computation to sort of realize that there's a whole lot of what I do is data cleaning, and I try and do it algorithmically as much as possible so that I'm not manually going into a data set with 600 variables by 2.5 million data points and editing those things. But yeah, it's definitely, it has a flow to it, and it's kind of because I'm a research institution, kind of have the luxury sometimes of being able to be you know what, I'm gonna just take a break from that rabbit hole that I've fallen down, and I'm gonna go work on this project for a little bit. So it's if I'm getting really tired of data cleaning, there are a couple other projects that I can work on where I can be visualizing, or if I'm just so sick of dealing with the Python talking to JavaScript, I can just kind of go back to data cleaning and just kind of it's sort of the breaking the sand garden of making your data nice and parsable.
Is there one website or a source that you would recommend to get actual good stats in your research? Yeah, a good reliable website that you would recommend.
Just like to have a data set to play with.
Yeah, like, do you recommend one that you use a lot?
Yeah, so in terms of toy data sets, I think Kaggle, I don't know if I'm pronouncing it right, but Kaggle, that's a great website where they have lots of like data science and data visualization challenges. So like the most common data set is the Iris data set or Titanic. Those ones are really nice because they're sort of already pretty clean and easy to work with. And then if you're looking for more sort of like in the wild data sets that maybe you want to like work on your skills of cleaning data or working with messy data, the Agency of Natural Resources, not to say that their data is messy, they've done a really great job of like pulling it all together, but that's more of like, so those are local data sets, so a lot of them are sort of gathered from lots of nonprofit and government groups, sort of aggregated together.
I have one more question, kind of backing up a little bit to you talking about the smoker and causation and correlation, and this is like sort of like a big question that's more sort of anybody can maybe answer it, but sort of like what's the point, right, of visualizing all this data? And this is something I've wrestled with. Like, I look at all these really fascinating data visualizations, or I think about doing that data visualizations myself, and in the end, if you can't necessarily find a connection between, correlation and causality, like, what's the point? What do you do with this data? What do you do with these graphs, right, in the end? I don't know. So, kind of, why are we so obsessed with visualizing data, and what does it really get? Is it really getting us anything, and what is it really getting us? Sorry.
No, I think it's a really good question, and I think that it's actually, so it's interesting because with every like new technological thing, we're kind of like, this is going to solve everything, like this is the answer, like all of our problems will go away now that we just know. But really the thing about machine learning and about data visualization is that it's not going to give us answers, and if we force it to give us answers, that's when we get this sort of dystopian situation where we're getting these like summary statistics, and we're like, oh, like, we've simplified it and we've gotten this, we can check a box, or we can categorize people, or this is the way that things are. Really the point of data visualization and of scientific inquiry is not necessarily to get answers, it's to better approximate some sense of reality, but it's also to inform further question asking. So it's this constant evolutionary exploratory process. And that can be really frustrating, actually, especially for people, friends of mine who are data scientists who are working in the business intelligence world, when they're working with a company and the company is kind of like, well, I want to be able to identify like 3 different types of customer, and I want to be able to project exactly what my revenue is going to be based off of these data points. And it can be challenging as a data scientist to explain that just like any science, it's not exact, and that it's only as good as the information that you're putting into it, and that no algorithm is going to give us the perfect answer, is going to give us sort of the ultimate reason for everything. You may recall the Hitchhiker's Guide to the Galaxy when they asked the computer for the meaning of life, and it spits out 42. Which some people theorize was actually 42 is the AC number or ASCII number of the asterisk, which is like a placeholder. So it's sort of like whatever you want it to be. But yeah, I think that's a great sort of lesson that we're learning every single time that a new technology comes out. It's like it's not giving us an answer; it's just giving us better questions.